Imagine a group of skeptical accountants sharing one notebook. No one fully trusts anyone else, but they all need the same record of what happened. Every new page gets a unique stamp that depends on the stamp on the previous page. If anyone tries to slip in a fake page, all the stamps after it no longer match. That, in spirit, is a blockchain. A shared ledger that many computers maintain together, where each new entry is locked to the past with a kind of digital fingerprint. The one big difference from familiar systems is this. There's no central bookkeeper, no bank, no server that everything runs through. The record exists because the network agrees it exists, not because one authority says so. Why should that matter? Because agreement is power. If a network of strangers can agree on who owns what or which contract conditions were met without a central referee, new kinds of digital cooperation become possible. Money that settles globally without banks, supply chain records that no single company can secretly change, and public logs where evidence can be checked by anyone. It isn't just about storing data. The hard part is getting a scattered crowd of machines, run by people with their own incentives to line up on a single history and to keep lining up over years. Let that sink in. Here's a simple picture to carry forward. Think of the blockchain as that shared notebook. Each page is a block listing recent transactions. Each page has a fingerprint, called a hash, that depends on the contents of the page and the fingerprint of the previous page. The group only accepts a new page after most members agree it's valid. On some networks, that agreement requires solving a costly puzzle. On others, it requires putting valuable coins at risk. So the simple version is blocks, fingerprints, and agreement. With those three ideas, a blockchain can turn an open network into a single source of truth. Now, gently into the mechanics, without rushing. A hash is just a digital fingerprint. Run any data through a hash function, and you get a short fixed-size output that looks random. Change even a comma in the input, and the fingerprint changes completely. The most common one in Bitcoin is called SHA-256. It's fast to compute, but impossible to reverse. If you see the same hash again, you can be confident the underlying data hasn't changed. What matters here is how hashes link blocks into a chain. Every block includes the hash of the previous block. That simple link means if anyone tampers with something buried 5 pages back, the hash of that old page changes, which breaks the next page, which breaks the next, and so on. Suddenly, the counterfeiter has to recalculate all the fingerprints from that point onward and convince the network to accept them. That's a steep hill to climb. There's also the question of what goes on a page. A block bundles a set of transactions, payments, updates to accounts, maybe smart contract actions, and a small header with metadata. That header includes the previous block's hash, a timestamp, and a compact summary of all transactions in the block. Many blockchains use a tree-like structure called a Merkle tree to compress that summary into a single hash, but the mental model can stay simple. The block has a fingerprint of the past and a fingerprint of its contents. Now comes the tricky part. How does the group agree on the next page? That's the consensus problem. Networks like Bitcoin use something called proof of work. The idea is to make proposing a new block expensive in terms of computation, so it's easier to follow the rules than to cheat. Miners collect transactions into a candidate block and then search for a special number, called a nonce, that makes the block's hash fall below a target value. There's no shortcut. It's like rolling a massive set of dice over and over until the dice rolls start with a long run of zeros. The first miner to find a valid nonce broadcasts the block. Other nodes check it. If the transactions are valid, the signatures verify, and the hash matches the target, they accept it and extend the chain. If two miners announce valid blocks at nearly the same time, the network may see a split for a moment. That's called a fork. The tie is broken when the next block is added to one of the sides. The common rule is to treat the longest valid chain, the one with the most accumulated proof of work, as the real history. There's something quietly elegant about that rule. Work accumulates like weight on a branch. The heavier branch wins. Proof of stake takes a different approach to the same problem. Instead of spending energy, validators put their coins at risk as a kind of security deposit. The protocol pseudo-randomly selects a validator to propose the next block, and others vote to confirm it. If someone tries to cheat, by signing conflicting histories or approving invalid data, their stake can be slashed, meaning a portion is burned or confiscated. The economic pressure discourages misbehavior without making the entire world do math puzzles. Different chains implement the details differently. Some add layers of checkpoints, committees, or finality gadgets, but the big picture stays stable. The network trades raw energy in proof of work for financial penalties in proof of stake. Both create a world where honesty is cheaper than cheating. Let's ground all of this with a concrete story. Suppose Alice sends 1 Bitcoin to Bob on the Bitcoin network. Bitcoin's design aims for a new block roughly every 10 minutes, and the mining difficulty is set so that, across the entire network, miners collectively try around 20 trillion nonces before one produces a valid hash. Today, that amount of work translates into a staggering global hash rate measured in exahashes per second, quintillions of tries, powered by energy on the order of entire countries. Alice's wallet constructs a transaction. It references the coins she owns, specifies Bob's address, and signs the message with her private key, which is a secret number only she controls. The signature is like a mathematical stamp that proves the transaction came from Alice without revealing the private key itself. Her wallet broadcasts that transaction to the network. It lands in a kind of waiting room called the mempool. A miner picks up transactions, including Alice's, and assembles a new block at height 800,000. The block header points back to block 799,999 with its hash. The miner then starts cycling through nonces. After countless tries, the winning hash appears, a long hex number starting with a string of zeros. The miner broadcasts the full block to peers, who instantly verify the signatures, recompute the hash to ensure it matches, and check that none of the transactions are double spends. Satisfied, they accept the block and extend their copy of the chain. Alice's payment now has one confirmation. Finality in Bitcoin's world is probabilistic. One confirmation means the transaction is in the latest block, but a fork could still replace that block. As more blocks pile on top, the chance of reversal drops sharply. 6 confirmations, roughly an hour, make a rewrite incredibly unlikely without controlling the majority of the network's mining power. In other words, the deeper something sits in the chain, the safer it is. Proof-of-stake chains define finality differently. They often have checkpoints where a supermajority of validators lock in a decision. Once a block is finalized, rolling it back would require collusion by a large fraction of stake and would trigger massive economic penalties. The security comes not from time and energy spent, but from the risk of losing locked-up capital. There's an economic standoff underneath all of this. If an attacker controls more than about half the mining power in proof of work, or a very large fraction of stake in proof of stake, they can try to build an alternative history and trick the network into accepting it. Pulling that off on a major chain is brutally expensive. Honest participants keep adding work or votes to the main chain, and the attacker's cost to overtake grows with every block. On large networks, the price tag to sustain such an attack can reach billions of dollars. So far, this has been about money, but the ledger can track more than balances. Enter smart contracts, small programs that live on the blockchain and run automatically when conditions are met. Picture an escrow that releases funds only when both parties provide a matching confirmation, or a marketplace where bids and asks are matched by code, not a company. The contract's logic is part of the shared history, and its actions are just as tamper-resistant as payments. Smart contracts are powerful because they combine public verifiability with automation. They're risky because code bugs become bugs in money. If a contract has a vulnerability, attackers can exploit it exactly as written. There's no customer service line on a public blockchain. The DAO incident in 2016, where a flaw allowed an attacker to drain around $50 million worth of Ether at the time, made that painfully clear. Good engineering helps, audits, formal verification, test nets, but the stakes remain high. Here's the thread to hold. The blockchain is a timeline. New events get accepted only if they fit cleanly at the end, and each event depends on everything behind it. That timeline exists not because any one participant is trusted, but because the group continually checks and enforces simple rules with deep consequences. A few common misunderstandings are worth clearing up. Public blockchains are not truly anonymous. They're pseudonymous. Addresses are visible, transactions are visible, and forensic techniques can connect activity to real identities. Specialized privacy coins add layers to obscure flows, but mainstream chains like Bitcoin and Ethereum are transparent by default. Another misunderstanding: blockchains are only for cryptocurrency. Digital money is the first major use case and probably the most battle-tested one. The core idea, though, is tamper-resistant agreement. That applies to any record where multiple parties want a shared truth without surrendering control to one of them. Supply chain logs, time-stamped publications, even voting systems if designed with care. Whether a blockchain is the right tool depends on whether decentralization and auditability are truly needed. One more: immutable doesn't mean instant. Recent blocks can be reorganized in the face of a fork or a coordinated attack. It's prudent to wait for confirmations proportionate to the value at stake. Coffee can settle after one block. A house should wait a lot longer. All of this comes with trade-offs. Speed and global consensus work against each other. Bitcoin processes a handful of transactions per second because it insists on a level of security and decentralization that requires time and redundancy. Visa's centralized system hits thousands per second because a small, trusted core can make instant decisions. The gap is real. Layer 2 solutions like payment channels and rollups try to push volume off the base layer while keeping the base layer as the final court of appeal, but the base layer itself is intentionally conservative. Energy is another trade-off for proof of work. It uses a lot, on purpose, to make attacks expensive. Critics focus on the footprint. Proponents argue it's the cost of an open, neutral settlement network and can be aligned with stranded or renewable energy. Proof of stake reduces that footprint dramatically by using financial capital instead of watts. It introduces different risks, largely around governance, stake concentration, and penalties for misbehavior. There isn't a free lunch, just different menus. There's also decentralization itself. More independent nodes mean more eyes checking every block and more diversity of control. That's good for resilience, and it raises coordination overhead. Fewer, more powerful validators can run faster, but they become easier to capture or coerce. The key idea is that blockchains invite the world to verify. That invitation comes with the cost of moving at the speed of the slowest honest participant. A quick mental checklist can help when using or evaluating a chain. For payments on proof of work, wait for a number of confirmations that matches the value at risk. The bigger the transaction, the more patience buys safety. Prefer networks where no single entity or small group controls a large share of mining power or stake. Decentralized power spreads risk. And when deploying smart contracts, rehearsal on test networks can surface bugs, because once code holds real money on a main chain, any flaw becomes part of the story the chain faithfully executes. Put differently, blockchains are social systems wrapped in math. People choose the software to run. People decide which chain to treat as canonical if two histories diverge. The cryptography gives strong guarantees about what's possible and what's detectable, but it's the incentives, rewards for honest blocks, penalties for bad behavior, and the market value of the token that keep the machine pointed in the right direction. Here's a quiet engineering marvel worth appreciating. There's no clock telling the network what time it is. There's no central coordinator handing out turns. Yet a global swarm of machines, owned by strangers, can end up with the same history, block after block, for years. No one gets to rewrite the past without paying an astronomical cost. Another subtle wonder. Tiny building blocks, hash functions, digital signatures, and simple voting rules combine into a system that creates digital scarcity, something computers weren't supposed to do. That synthesis is where a lot of the fascination comes from. Now, a few terms in plain English, just to confirm the mental map. A block is a bundle of recent transactions plus a header that points to the previous block. A hash is a fingerprint of data, easy to compute, impossible to predict, and instantly different if the input changes. A consensus mechanism is the rule the network uses to agree on which block becomes part of history. Proof of work spends energy to make lying expensive. Proof of stake puts money on the line so dishonest validators get punished. A smart contract is code that owns assets and moves them according to rules encoded on-chain. Stepping back, where does this fit in the real world? A public blockchain is a base layer, like a settlement network. It's slow by design, so it can be trusted by anyone. Faster experiences can be built on top. Wallets, payment channels, application layers, while the base layer acts as the anchor that everyone can check. It's similar to how international wire systems settle large movements of value less frequently, while consumer payments ride on higher speed rails that eventually reconcile. What about private or permissioned blockchains run inside a company or a small consortium? They can be useful for audit trails and shared workflows where there's some trust but a need for tamper evidence. They don't solve the open internet problem of trust among total strangers, and they don't need the same energy or decentralization. The design goals are different. Security also has a social layer. Software upgrades require coordination. Disagreements can lead to forks, two communities maintaining two versions of history if they care about different trade-offs. The famous split of Ethereum and Ethereum Classic after the DAO hack showed that values matter. One community prioritized reversing the exploit, the other prioritized keeping code as written. Both paths are consistent with the core mechanism. Choice lives above the math. It's helpful to think in risks instead of absolutes. A block just mined is like wet cement. It firms up as more blocks harden above it. On proof of work, time and energy add weight. On proof of stake, validator votes and finality checkpoints add lock-in. A transaction isn't unchangeable the instant it appears, but with patience, the probability of reversal can be dialed down to nearly zero. To wrap the mental model into a handful of pictures, remember the shared notebook. Each page lists new entries and carries a fingerprint of the page before it. The group only accepts a new page if it follows the rules. In proof of work, that acceptance requires real computational effort that anyone can verify, like seeing the ink stamp. In proof of stake, acceptance is backed by deposits that can be burned if validators cheat. As pages accumulate, revising an old page becomes prohibitively expensive. The promise and the limits sit side by side. Blockchains let open networks agree, reliably, without a central editor. They do it by making the past heavy and the present verifiable. In exchange, they give up speed and take on complexity. Not every problem needs that trade. For problems that do, like neutral money or public settlement, the mechanism is surprisingly sturdy. So if nothing else, walk away with this. The magic isn't in buzzwords. It's in three simple forces working together. Link every page to the one before with a fingerprint. Make it costly to propose bad pages. Reward the network for choosing the same honest history. Everything else, the tokens, the apps, the debates, grows from that core. If this helped, a like and subscribe helps us make more of these.